Pluto, a distant and enigmatic celestial body, was once part of our solar system's planetary family. However, recent alarming statements from prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku have thrust Pluto back into public attention. They have made a startling revelation: Pluto might be on a potential collision course with Neptune. But how could such an event happen, and what would the consequences be? Is this a rare cosmic anomaly, or is there something more to this imminent cosmic impact? Join us as we explore the possibilities of a potential Pluto-Neptune collision. Pluto, once classified as a planet, but later redefined as a dwarf planet due to its peculiar orbit, continues to captivate the scientific community. According to recent research by leading scientists, Pluto's trajectory is dangerously close to Neptune's orbit. Renowned astrophysicists like Tyson and Kaku are raising alarms about the potential for a catastrophic collision between these two planets, a scenario that could pose a significant threat to Earth. Unlike any other planet in our solar system, Pluto's journey around the Sun is highly unusual. It takes a remarkable 248 years to complete just one orbit. Since its discovery in 1930, Pluto hasn't even finished one full orbit, which adds to its mystique. But Pluto's orbit is not just slow, it's also highly elliptical, vastly different from the more circular orbits of the larger planets. To complicate things further, Pluto's orbit is tilted at an angle of 17 degrees to the plane of the solar system. This inclination makes its path much more extreme than the other planets, adding layers of complexity to its movement. One of the most intriguing aspects of Pluto's orbit is its interaction with Neptune's orbit. For roughly 20 years of each orbit, Pluto comes closer to the Sun than Neptune does, defying what we might expect based on the relative positions of planets in our solar system. This naturally raises the question: why hasn't Pluto collided with Neptune? The study of Pluto's orbit began shortly after its discovery. Early astronomers were puzzled by its strange path. Unlike other planets whose orbits are somewhat aligned with the ecliptic plane, Pluto's orbit stood out due to its steep tilt and elliptical nature. The realization that Pluto's orbit crosses Neptune's was a major point of scientific curiosity. Despite these irregularities, the stability of Pluto's orbit is a remarkable feature of space mechanics. The phenomenon known as the three-body problem comes into play when studying the movements of Pluto, Neptune, and the Sun. This problem involves understanding the way three celestial objects move and affect each other through gravitational forces. Predicting their paths is a complex task, and this is where terms like AIML libration, scope libration, and VZK become relevant. AIML libration refers to the fact that when Pluto crosses Neptune's orbit, it remains at least 90 degrees away from Neptune, ensuring their paths do not intersect. Scope libration describes the vertical movement of a celestial body in its orbit. For Pluto, this means that when it gets closest to Neptune or any other large planet, it is positioned above the plane of their orbits, offering extra protection from potential collisions. VZK wobbling, named after researchers VZ and K, explains how Pluto, Neptune, and the Sun's gravitational pulls influence each other, keeping Pluto's path stable despite its apparent erratic behavior. Even though Pluto's orbit may seem unpredictable, this wobbling mechanism helps maintain its steady motion over long time scales. These complex forces help ensure Pluto's orbit remains stable, preventing it from crashing into Neptune or deviating wildly. The three-body problem is essential for understanding how orbits change due to the gravitational influence of multiple objects. Studying this helps us gain a deeper understanding of Pluto, our solar system, and even distant celestial bodies and their stars. Mathematical simulations conducted in the late 1980s revealed that although Pluto's orbit has these stabilizing factors, it is still chaotic. Small changes in its starting conditions could lead to significant variations over millions of years. Despite this inherent chaos, Pluto's orbit remains stable over incredibly long time scales, effectively keeping any potential disruption in check. Recent computer models have provided new insights into how the gravitational influences of giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit. These models show that Pluto's relationship with Neptune is unique. For every 2 orbits that Pluto completes around the Sun, Neptune completes 3. This relationship helps to stabilize Pluto's orbit. Jupiter's gravity plays a key role, as does Saturn's, providing additional stability. These simulations demonstrate that Jupiter's gravitational pull alone is strong enough to ensure Pluto remains in a stable orbit for billions of years. Together, Neptune, Jupiter, and Saturn work in tandem to keep Pluto safely on its course, avoiding any catastrophic collisions or other disruptions. These gravitational forces are essential for maintaining order in the solar system. Without them, the system would be much more chaotic, with planets and dwarf planets like Pluto potentially colliding or being ejected from their orbits. Understanding Pluto's orbit is crucial to gaining a clearer picture of our solar system's dynamic nature. Pluto's case serves as a prime example of how even the most seemingly unstable orbits can achieve stability through the intricate interplay of gravitational forces. It also underscores the importance of continuous observation and exploration to better understand our place in the universe. The study of Pluto and its orbit illustrates the unpredictable nature of celestial mechanics. The concept of orbital chaos, referring to the extreme sensitivity of a body's orbit to its initial conditions, is clearly visible in Pluto's case. Even the smallest change in Pluto's position or speed could significantly alter its orbit over time. Simulations have played a pivotal role in helping researchers understand Pluto's motion. These computer models use complex mathematics to simulate how Pluto and other celestial bodies interact gravitationally. By tweaking small variables, astronomers can see how tiny changes can drastically alter Pluto's long-term orbit. Despite the apparent chaos, Pluto's orbit remains relatively stable, enduring for billions of years. This demonstrates that while its path may seem chaotic, there is an underlying order to it. Predicting celestial events, especially those involving chaotic orbits like Pluto's, is a formidable challenge. The unpredictable nature of these systems means that long-term predictions are fraught with uncertainties. While simulations are invaluable tools for understanding and forecasting the movement of celestial bodies, they also highlight the limitations of our predictive capabilities. Any slight error in initial conditions can lead to drastically different outcomes, making precise predictions nearly impossible. The chaotic nature of Pluto's orbit serves as a reminder of the constantly evolving and dynamic universe we live in. Even as we make great strides in space exploration and understanding the cosmos, Pluto's orbit reminds us of how much is still unknown. Understanding the gravitational interactions of giant planets on Pluto provides important insights into the broader dynamics of the solar system. It reveals how the positioning of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. Pluto's orbit is unique but stable. Pluto's highly elliptical and tilted orbit is very different from the other planets. It crosses Neptune's orbit, but a 3:2 resonance with Neptune. For every 3 Neptune orbits Pluto completes 2 prevents collisions. Why Pluto won't collide with Neptune? Orbital resonance. Pluto and Neptune are locked in a gravitational dance that ensures they never come too close. Inclination scope librations. Pluto's orbit is tilted and moves in such a way that even when it crosses Neptune's orbital plane, it remains at a safe distance. Gravitational influence of Jupiter and Saturn. These planets play a stabilizing role, preventing Pluto from deviating significantly. While Pluto's orbit is chaotic over extremely long time scales, millions to billions of years, models show that its current path is stable. No foreseeable collision with Neptune is predicted based on current simulations. Advances in astrophysics continue to refine our understanding of celestial mechanics. The study of Pluto's orbit helps scientists understand exoplanetary systems and broader gravitational interactions in space. Despite dramatic claims, there is no credible evidence that Pluto is on a collision course with Neptune. While Pluto's motion is complex, the stabilizing forces at play make a direct impact highly unlikely. Scientists like Neil deGrasse Tyson and Michio Kaku discuss Pluto's orbit to highlight the unpredictability of celestial mechanics rather than suggest an imminent catastrophe.